Okay, let's do this quicker. That's a 2 by 2. What you do is start from the characteristic equation, which is A minus Ri equals 0. That's 6 minus R2, and give you 6 minus R plus 6 equals 0. And then R minus 3, R minus 4. And then the second one. For that one, R equals 3. That's a kind of review of the eigenvalue. And then you put a 3 here, 3, put a 3 here, and the 2. And then you get the A1, B1, we call the eigenvector. One thing is sure, if you are right, these two equations are the same, right? If not the same, nothing you can have but a 0. I'm not interested about that. So you got this 2A1 minus 2B1 equals 0, A1 equal B1. I just let it equal 1. You can be a longer or shorter, and then A1 must be 1. Then your first eigenvector V1 is going to be 1, 1. Then your first solution is going to be E3T 1, 1. And similarly, for the second one, you put the R equal 4, what you get is 3 minus, okay, 4 minus, that's 2, negative 3, 2, negative 3. And then you get the same equation, 2A2 equals 3B2. In order to make an integer, I take the freedom, let the B2 equal 2, then A2 equals 3. I get my second vector is 3, 2. Now what you get? Your second solution is e to the 4t 3, 2. General solution is e to the 3t 1, 1, C1, C2. That's the same as this. So that's how you solve equations by hand. Of course, that's a toy, 2 by 2. You're not going to do it 10 by 10 by hands. This is the 3 by 3. I don't have time, but I run through the procedure. That's the characteristic equation. It's a cubical. You got this, and there's a quadratic. You have the solution 0, negative 3, and 2. And then for each one, let's say put a 0 in. Put a 0 in, you basically, that's 0. You times this itself, A1, B1, C1. Among these three equations, see, these are the same, right? You only have two equations. That's how you get the non-zero solution here. And then you get the R equal negative 3. You get this one, get this one. And then your solution, that's the first one, e to the 0 is 1, right? E to 0t. And that's nothing here. Second one, third one. This is your solution. That's your solution. And you can check at least one. If you put a constant, you definitely get a 0. That's like this one. So you solved this homogeneous system. So far, you only see all the real solutions. How about you get something like this? Let me show you an example quickly. Negative 1, 1. That's your A. And what you're going to get is R, A minus R equals 0. Then it's r negative 1 equals 0. And your r is going to be imaginary. What you're going to do? If this is a real physical science application, you say, how I can on Earth get an imaginary, especially when you have a spring mass system. Everything is real. Thanks for Euler. This Euler formula is just to say, don't worry, if you get imaginary eigenvectors, it really ends up with the trigonometry function. When you select the good cosine, the constant C1 and C2, they really end up with a trigonometry function. So the next theorem simply tell you if this A is real value, there's no imaginary here. There's no imaginary here, no imaginary here. Nevertheless, you got this R, which is imaginary, have this beta not equal 0, just like the example I showed you here, which is R equals positive or negative I. That means alpha equals 0, beta equals 1. That's imaginary. That's kind of weird. But the theory says, don't worry. If that's your case, number one, those imaginary complex solutions always come in pair. Just that's why it's called conjugate. They always come together. So if this is an eigenvalue, this must be also an eigenvalue. If this is an eigenvector, A and B are real, A, B are real, and then this A plus IB also must be an eigenvector. So the eigenvalue come to pair, and the eigenvector come in pair. When they're paired together, look just like here. If you pair them together, they make it real. You see, e to the ix, e to the negative ix, make it cosine. E to the ix minus this divided by 2i, make it a sine. So they always come to pair. So in the end, your solution, instead of imaginary, which is not realistic, you get those things. E to the alpha t, that's really it's a decay or growth function. It's just talk about the amplitude. And these are the trig function, a real vector, trig function. So in the end, what you get is a real vector function. A typical phenomenon is the spring mass system. You always get those kind of phenomenon. You always get this kind of phenomenon. We call it attenuating oscillation. That kind of function is right here. Is the decaying energy, amplitude. And the trigonometry functions here with the same quasi-frequency go down, but just the loss energy. So that reconcile the problem to the physicists. So I have 10 minutes. Look at an example here. It's a 3 by 3. In this case, when I get the characteristic equation, I get one real solution and two imaginary solutions. I think that's a little bit wrong. Positive I and the negative I, it's really minus 1 square. And then for this real solution, nothing new. You just got this vector, and your solution is ET 0, 1, 0, as we did. For the imaginary solution, when this equals 1 minus I or plus I, you put it here, then you get use the 1 minus I. You put it the 1 minus I, and then 1 cancel out 1. You got the I 0, 1, 1, I 0, negative 2, 0. Basically, you got two equations. This one is the same, redundant. So you got the IA minus C plus C equals 0. A plus IB equals 0. How are you going to solve this? Take advantage of the free variable. I let the C equal negative IA, then B I equals negative A. I let the A equal negative 1. Then my C is going to be negative I. B is going to be A equal negative 1, negative I. That's not an exact look at this, but we can always have different representation because your freedom of choice. I think the book maybe take that one equation. So in the end, you get one vector. Let me get mine to see how mine can write. Mine is negative 1, negative I, and then I can write it as negative 1, 0, 0. That's the real part. I, 0, negative 1, negative 1. They look differently, but you can change when you rewrite it. So once you get this solution, what I emphasize is the next step. How do you write this into real solution? That's the question. And the answer is follow the formula. You get this first solution is e to the alpha t, and C1 cosine beta t a minus sine beta t b. That's the first one. The second one is sine beta t a plus cosine beta t b. And what is your beta? Your alpha equals 1, beta equals 1, if I remember right. This is negative 1, 1, 0. I copied it wrong. So change this into negative 1, 1, 0, negative 1, 1, 0. Now we check. Yes, negative cosine t and negative sine t, negative make a positive. That's the first one. Second one, negative sine t minus cosine t. That's the, row by row you check. And the second one is 0, negative sine t here. And the second row is cosine t here. And the third one is 2 cosine t here. That's 0 here. And the 2 sine t here. So that's these two. And the first one we remember is this. And it's right here. You have 3 of them. They're all real. That's the whole point.